Okay, this is going to be me going over the unit for review. The height above the ground of a passenger on a Ferris wheel t minutes after the ride begins is modeled by the differentiable function h, where h of t measures is measured in meters. Which of the following is an interpretation of the statement of h prime of 7.5? So first of all, h prime is going to be measured in meters per minute. So keep that in mind. This is supposed to be measured in meters per minute, and this 7.5 is referring to 7.5 minutes. And so here, option A says the passenger's height above the ground is measured in 15.78 meters per minute. So that's correct. When the passenger is 7.5 meters off the ground, that is incorrect right there. We're not talking about 7.5 meters. We're talking about 7.5 minutes. The passenger's height above the ground is increasing, okay, by 15.708 meters per minute, 7.5 minutes after the ride begins. That sounds right there. Just to check the other ones, the passenger is this refers to meters per minute, not meters. So that's not the correct units there. And then the Ferris wheel is turning at a rate. No, we're not talking about the rate at which the Ferris wheel is turning. Nope. We're talking about the feet above we're talking about the height of the passenger above the ground. Okay, example 2. A customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by the differentiable function F, where F of t is measured in gallons per second. So it's measured in gallons per second. That's what F is measured in. And t is representing seconds since pumping began. Which of the following is the best interpretation of F prime of 90? Okay, so the amount of change in gallons per second in the rate at which gasoline is pumping during the first 90 seconds. So the amount of change in gallons per second. It's not gallons per second. The derivative at 90 seconds is going to be equal to this, but it's going to be in gallons per second. So that's what I'm looking for. The amount of gasoline in gallons, nope. Not going to be measured in gallons. The rate at which gasoline is being pumped in the tank in gallons per second. Nope. Okay, the rate of change of the rate. Yep, that sounds right. So it's the rate of change because the rate of the flow of gasoline is already F of t. So we're doing the rate of that. So the rate of change of the rate at which gasoline is being pumped into the tank in gallons per second. Yes, in gallons per second. 90 seconds after pumping begins. Yep. Okay, the position of a particle moving along the x-axis is given by this function right here. This is a position function. Keep that in mind. It's position. For time t is greater than or equal to 0. When t is equal to pi, the acceleration of the particle is, so I need the acceleration and I have position. So I'm going to take the derivative, so that would only give me v of t though. So v of t, the velocity, is equal to x prime of t. And that's going to be equal to 2 cosine of 2t plus 3 sine of 3t. Okay, and then the acceleration is going to be equal to the first derivative of velocity, which is going to be equal to the second derivative of position, which is going to be equal to that negative 4 sine of 2t, and then plus 9 cosine of 3t. And then I want a of pi. I'm trying to find the acceleration at pi. That's going to be equal to negative 4 sine of 2 pi plus 9 cosine of 3 pi. Sine of 2 pi is 0. Cosine of 3 pi is negative 1. So this is going to be 0 plus 9 times by -1, which is going to be equal to -9. No units are mentioned here, so we'll just leave that. -9 is the acceleration. A particle moves along the x-axis with velocity given by this function here, from -3 to 3. How many times does the particle change directions as t over this interval? Okay, so this is velocity. I always like to make sure that I know what function I have. This is a velocity function. Okay, and so what does that mean in terms of changing direction? So the position changes direction, or the particle changes direction when velocity changes from positive to negative. So what I'm going to do is I'm going to graph this right here and check and see where it changes directions. So I'm going to open my calculator. All right, so we're going to have 3x to the 4th. So 3x raised to the 4th. And then we have minus 11x squared plus 9x minus 2. Okay, and I'm going to, well, in my window, let me change this to be -3 for the minimum. For the maximum, I'll do 3. Let's graph it like this right here. And so, so this is, what the heck is that? I don't need that right there. Okay, so here is my velocity curve. And so I can see velocity on the left side. Can I click in this? So like right around here, velocity, so velocity here is positive, but then it's going to turn to negative. And then over here, pretty sure it stays negative. Even if it does touch right there, it still stays negative after touching, which means it doesn't change direction, but velocity is negative, and then finally it changes to positive. And so that's 2 times where the particle is going to change directions, because that's where velocity changes signs. And so that's going to be twice. And the reason why is because that's where there are 2 times where the velocity function changes from positive to negative or negative to positive on that interval right there. Okay, a velocity of a particle moving along the x-axis is given by this function right here. So again, we have a velocity curve for t is greater than or equal to 0. Which of the following is true about the particle at time t equals 1.5? The acceleration is negative, speed is decreasing. The acceleration is negative or positive, speed is increasing or decreasing. So what we're going to do now, so you can do this by hand, or if you have a calculator, you can do that too, and I'd like to kind of just talk about both. So if you're doing it by hand, as far as speed goes, so speed is increasing when both, we'll just say we'll say velocity and acceleration have same sign. And speed is decreasing when they have opposite sides. So V and A have opposite signs. Okay, so same sign, so they're both positive, then speed is increasing. Both negative, speed is increasing. One's negative, one's positive, speed is decreasing. And so we're trying to check the speed at 1.5. So let's go ahead. So right now you can just plug in 1.5 in here by hand, and we're basically just trying to see if it's positive or negative, okay? But then we also want to find the acceleration, because we need to check to see if acceleration is positive or negative. So you can plug this, you can plug this in here to see if you get positive or negative for velocity. And then you can take the derivative of that, and then you can plug 1.5 in to see if that's positive or negative. So I'm just gonna do this with a calculator though. So what I like to do, to plug values in, I'm just gonna do 1.5. Was it 1.5? Yeah, 1.5. Store as x value, so I'm going to use that right there, and then I'm going to type in the function. So it was 1 minus t to the third, so parentheses 1 minus x to the third divided by 1 plus x, I believe is what it was, right? Okay, I'm going to click enter, and I get negative 0.95. So v of 1.5 is equal to negative 0.95. Okay, and then you could just use your calculator to do the derivative. Oh man, this calculator does not like doing exponents though. So if I go 8, so you can plug in 1.5 right here, and then I'll try doing this. So parenthesis, oops. And then close parenthesis, and then I'm gonna, no, okay, maybe, divided by parenthesis, close parenthesis here, I'm gonna do 1 plus x, and then I'm gonna go in here, and then I'm gonna do 1 minus x to the third. I think I outsmarted that. Sweet. Okay, so then I get that the acceleration at 1.5 is negative 2.320. So a of 1.5 is equal to negative 2.320. Is that what I said? Okay, so both are negative. That means speed has to be increasing, and acceleration is negative, so it has to be b right there. Okay. A particle moves along the x-axis so that at time t is greater than 0, its position is given here. At what time is the particle at rest? So I have myself the position function, and I want to know when the particle is at rest. So that's going to be when v of t is equal to 0. So I'm going to need to take the derivative of this. So v of t is equal to 6t squared minus 42 t plus 72, and I'm just gonna graph that. If I could do this, if you could, oh yeah, you can factor this if you want to do that instead. I would say, like, up here in this problem, we're basically doing the same thing, except the difference between question 4 and question 6 is that this just wants to know when v of t is equal to 0, but this question specifically, when it changes directions, it has to change from positive to negative, negative, positive. So while the position is at rest, at the same time it changes directions, it's not always the case that it changes directions. Okay, so if this could have been factorable, which I don't think this is very factorable, you would have to use like the irrational roots theorem, and then maybe synthetic division. That's if there are any rational roots, the roots might be irrational. So that's why I just graphed it. But yeah, I'll show you how you can do both here. So that is the 6 going to 72? So 72 divided by 6, 72 divided by 6, it does, and then 42, that goes into 6, goes into 42, yeah. Okay, so, but I'm just gonna graph it, okay, and so 6t squared, so 6x squared, was it minus or plus? Minus 42, and then was it plus 72? Yeah, plus 72. Window, I'm going to set it to zoom, we're going to do 3. Okay, so here it is. You can kind of already tell just by looking at it. So at t equals 3, t equals 4. But if you need to actually, so second trace, you can go to 2 and find the zeros. So put your cursor to the left, click enter. Put your cursor to the right, click enter. and then if it asks for a guess, you can just do enter. But you can see there that it's at x equals 3, and so at t equals 3. Okay, and then for the sake of showing you the alternate way, you can just factor this. So I can take out 6. I'm going to get t squared minus 7t plus 12. Right? Okay, and then that's going to be equal to 6. That's going to be equal to t minus 4 and t minus 3. And when that's equal to 0, the velocity is equal to 0, right? So that's at t equals 4 and at t equals 3. So t equals 4. So that's whenever the particle is going to be at rest. All right, so the radius of a circle is increasing at a constant rate. So the radius of the circle is increasing. I'm going to call that dr dt at a constant rate of 1/2 meters per second. What is the rate of change in the circumference of the circle? So dc dt. So we're trying to find the rate of change of the circumference. When r is equal to 4, we're going to see that that actually doesn't matter, but circumference of a circle is equal to 2 pi r, and then if I take the derivative, the change in the circumference with respect to time is going to be equal to 2 pi dr dt, and so dc dt is going to be equal to 2 pi times by 1/2, which is going to be equal to pi, and that's going to be in meters per second. Don't know why I have that right there. So pi in meters per second. Now, again, you can kind of see that this didn't really play a role, and it doesn't have to. You don't have to use that, but yeah, it's irrelevant to the rate of change of the circumference. Okay. A person 2 meters tall walks directly away from the street light that is 8 meters above the ground. If the person is walking at a constant rate and the person's shadow is lengthening at the rate of 4/9 meters per second, at what rate in meters per second is the person walking? So to kind of give an illustration right here, so we have the street light. Okay. Say that the person's like right here. So the street light 8 meters tall, and then the person walking is 2 meters tall. Okay, now the distance from the street light to the person I'm going to call x, and then the distance or the length of the shadow I'm going to call s, which makes the total distance right here x plus s. And so I know a lot of people are having struggles with this type of question right here because of proportionalities, but there are 2 triangles in play here, and here are the 2 triangles. So the reason why these triangles matter is because these proportions matter. It means that the ratios are the same. So if I have here 2 triangles and they share the same angles, so this triangle right here, all 3 angles in this triangle are the same as all 3 angles in this triangle through some proofs that you might have forgotten through SM2 or in geometry. Okay, so but in any case, we're here and it's happening, so it's just how it is. So but what we have learned is that if the angles are the same in 2 different triangles, then their side lengths are proportional to each other. So we can use that to set up an equation. We can say that the heights of these triangles, the ratios of the heights of these triangles, which would be 8:2. So 8:2 is going to be equal to, now this 8 right here represents the height of the larger, and this 2 represents the height of the smaller triangle. And then we're going to compare that with the bases. So the base of the larger triangle, which is x plus s, is going to have the same, so the base of the larger triangle divided by the base of the smaller triangle is going to be the same ratio as the heights. And so that's basically what we just set up here, that they're going to be proportional to each other. So that helps me. So this right here is going to be 4 is equal to x plus s over s. That means 4s is equal to x plus s, which means 3s is equal to x. So with that being said, I've now related here the length of the shadow and the length of the distance between the streetlight and the person. And so right here, I can take the derivative, which would be 3 ds dt equal to dx dt. Okay, we don't know what these are right here, these lengths are, but we don't need to know them because the rates can be compared to each other without having them. And so we're trying to find, we know that right here, that the person's shadow is lengthening at a rate of 4/9. So that's ds dt. So 3 times by 4 over 9 is equal to dx dt, which is the rate at which the person is walking. Okay, and then that just means that dx dt is going to be equal to 4/3, and that's going to be in meters per second. So that's how fast the person is walking away from the streetlight. Okay, so the length of a rectangle is increasing at a rate of 8 centimeters. So if we have this rectangle, okay, so this rectangle is growing. So the length is growing and the width is growing, and the length is growing at 8 centimeters per second, and the width is growing 3 centimeters per second. And when the length is 20 and when the width is 10, what is the rate of the area? So the area of a rectangle is going to be length times by width. Keep in mind that both of these are functions of time. All of these are functions of times, but whenever I take the derivative of this part right here, that means I'm going to need to use the product rule. So dA dt is going to be equal to the first times by the derivative of the second plus the derivative of the first times by the second. Okay, and then I should have all these values right here. So this is going to be equal to the length, which we said was 8 times, the length of the rectangle is 20 times by the rate of change of the width, which would be equal to 3, right? And then plus the rate of change of the length, which is going to be 8 times by the width, and the width is 10. So that's equal to 60 plus 80, which is going to be 140. And the units here, we're talking about area, that's going to be in centimeters squared per second. So that's the rate of change of the area. Okay, 10, let f be a differentiable function with f of 2 equal to 3 and f prime of 2 equal to 1/2, using the line tangent to the graph of f at x equals 2 as a local linear approximation for f. What is the estimate for f of 1.8? And so I'm going to make a tangent line. So y minus 3 equal to 1/2 and x minus 2. And this right here we're saying is about approximately equal to f of x around values of 2, around values of x equals 2, and we want to approximate f of 1.8, so I'm going to plug in 1.8. So y minus 3 is equal to 1.2. If I plug in 1.8 right here, that's going to be equal to negative 0.2. And then y is going to be equal to 1/2 times by negative 0.2 plus 3. And then you can go ahead and I'm just going to let you guys punch that into a calculator, and you'll get it right there. Okay, for 11, so we're also doing another one of those problems right here. So what is the approximation for the cube root of 10? About x equals 8. Okay, so that's important to note. So we're going to make a tangent line on this function right here. So that's going to be y minus y1, and y1 is going to be the cube root of 8 equal to, now we're going to need f prime of 8 here. We need the slope of this graph at x equals 8, and then we're going to have x minus 8. So first of all, let me do f prime of x. So f prime of x is going to be equal to, let me rewrite this as x to the 1/3. So it's going to be equal to 1/3 x to the negative 2/3, which is going to be equal to 1/3 x to the 2/3. And then, so that's f prime of x, and f prime of 8, which is what I want, is going to be 1/3 times by 8 to the 2/3, which is going to be equal to 1/3. So if I'm doing this, 8, let's say the cube root of 8. You can do either one first. So you can do 8 squared, which is 64. And then you can do the cube root of 64, which would be 4. Or you can do the cube root of 8, which would be 2. And 2 squared, which would be 4. So either way, I get that, which is going to be 1/12. So I get y minus 2, because that's the cube root of 8, is equal to 1/12 times by x minus 8. Okay, now this right here is all approximating the cube root of x around values of x equals 8. So we want to approximate this at x equals 10. So we want to approximate that at 10. So y is going to be equal to 1/12 times by 2 plus 2, which is going to be 1/6 plus 2, ... You guys can use a calculator, or you can give an exact expression, whichever one works for you. Okay. Let f be the function defined as such here. Let g be a differentiable function with derivative given here. It is known that the limit as x approaches infinity of g of x is equal to infinity. Find the value of the limit here. So the limit, I'm going to first show the limit as x approaches infinity of f of x, which is equal to 2x plus 3e to the negative 5x. So that right there is going to be equal to infinity plus 0. This part will be infinity. This part will be 0, because 3/e to the 5x, as you let x approach infinity, is going to be equal to 0, because the denominator will outpace the numerator. So it's still going to be infinity, and we know that the denominator is also going to be infinity, so we can use L'Hopital's rule. So the limit as x approaches infinity of the derivative of f of x, so that's going to be 2 plus 3e to the negative 5x times by negative 5, all over g prime, which is already given to us. Okay, and then let's evaluate the limit here. So the limit as x approaches infinity of 2 is going to be 2, but for this part, it's going to be 0. So it's going to be equal to 2 plus 0 over 0, because as x approaches infinity there, again, you're going to get 0. And then the limit as x approaches infinity of 5 over x is going to be 0, but that's going to be 4 plus cosine of 0, which is going to be equal to 2 over 4, and cosine of 0 is 1, so it's going to be equal to 1/2. Okay, the third derivative of the function f is continuous on the interval from 0 to 4. Values for f and its first 3 derivatives at x equals 2 are given in the table. What is the limit as x approaches 2? Okay, so if I show here, the limit as x approaches 2 of f of x is going to be equal to f of 2, which would be 0, and if I plug in 2 here, I'm going to get 0, so I can use L'Hopital's rule. So we'll do the limit as x approaches 2 of f prime of x over 2 times by x minus 2. Okay, now let's apply the limit here. So f prime of 2 is still going to be 0, and if I plug in 2 right here, I'm still going to get 0. So then I can still use L'Hopital's rule because I still get an indeterminate form. So the limit as x approaches 2 of f double prime of x over, that's just going to be 2. The derivative of this whole thing is just going to be 2. And then if I plug in 2 here, f prime of 2 is going to be equal to 5 over 2, so that's going to be our limit. And then for this part, the limit as x approaches 0, e to the 0 is going to be 1 minus cosine of 0 is going to be 0 minus cosine of 0 is 1. So e to the 0 is going to be 1 minus cosine of 0, and cosine of 0 is 1 minus 0 over 0 minus 0, so it's going to be 0 over 0. So L'Hopital's rule, limit as x approaches 0 of e to the x, and that's going to turn into plus sine of x minus 2 over 2x minus 2, and if I plug in 0, I get 1 plus 0 minus 2 over negative 2, which is going to be equal to 1 minus 2 over negative 2, which is negative 1 over negative 2, which is going to be 1/2. Okay. So as far as the first FRQ, I didn't really give any specific problems. I don't really have anything on that to give, okay? Sorry, but I did state at least what you should be prepared with to know, so hopefully that's good enough. Okay, and then I have this right here. So we have particle P moves along the x-axis so that its position at t is greater than 0 is given here. So we have the position of the particle P, and we have a second particle Q. It also moves along the x-axis, and we're also given its position, and we're given the velocity of the particle P. So it says find the velocity of particle Q. So that's just going to be, so we'll say x, or we're going to say v q of t is going to be equal to 3t squared minus 6t. Okay, so that would be that part right there. Find the acceleration of ax. So find the acceleration of particle q. So that's going to be a q of t. That's going to be equal to 6t minus 6. And the second part says determine where the speed is increasing and decreasing. So we've already covered this concept. So we need to check the signs of both v and q to see when it's negative. So you can do this with a graph or with some factoring, but I'll show you with a graph right here. So let's graph the velocity. So 3t squared minus 6t. And if we graph it, so here we go. Also note that we don't need negative values. We're talking about when t is greater than 0. So if you want to adjust that in your window, we can say for x minimum value, we'll put 0. Okay, and so here we can see from this graph right here that the velocity is going to be negative from 0 to 2, and then it's going to be positive afterwards. Okay, now you could do that right here just by factoring this. So if I factored this right here, that's going to be equal to 3t, and then it's going to be equal to t minus 2. So at t equals 0 and t equals 2 is when the velocity will be 0, and we can see that here. Okay, and I can also see that this is a parabola. So if I'm doing it by hand, I can think about it like so this right here would be a line for the velocity, and then at t equals 0 and at t equals 2, I can think about this visually that the graph is positive. It's a positive parabola, so this is what v of t would look like. And again, I can see that velocity is negative here but positive here, so I can see velocity is negative here and positive here. Now as for acceleration, okay, well I'm gonna think about the graph of acceleration. So if I set this equal to 0 to try and find when acceleration is going to change signs, I get that t is going to be equal to 1. So we have t equals 0, t equals 1 right here. So at t equals 1, and then you can also see that this is a linear line, so it's going to look like this right here. We can graph that here if you want to, but you're going to get 6x minus 6, and if we graph that right there, so you can see that we have acceleration is negative from 0 to 1, and then it's going to be positive. So acceleration is negative here and positive here. So if we want to see when speed is increasing, velocity and acceleration have to have the same sign, so you can see that they're both negative from 0 to 1. So increasing from 0 to 1, and it's also increasing after 2, from 2 and onward. They're both going to be positive, so that's going to be from 2 to infinity. And then decreasing, so decreasing whenever they have opposite signs, so you can see that's going to be between here and here, so between 1 and 2, because acceleration is positive but velocity is negative there. So speed is going to be decreasing from 1 to 2. So there you go. You can see that just right there. Now, if we were to go back to just having the graph of v of t, you could say 3, so it was 3x squared minus 6x. And if we go back to graphing it, you can also kind of see it from this graph right here. So at t equals 1, you can see where it has a minimum. Let me show that here. So the graph looks like this. This is the graph of velocity. Okay, you can see if this is the velocity curve, you can see that acceleration is negative here because that's when velocity slope is negative. So the slope of our velocity is negative here, hence that's why acceleration is negative there. And you can see that velocity is positive here. And so if you just want to look at v, you can also do that, but you also have to know whenever the minimum is occurring. So, but in either case, there's different ways to do this or look at it, but I think this gives a lot of explanation. So as far as if it's asking for a reason, you can say this is where velocity and acceleration have same sign. And then you can say here, the velocity and acceleration have opposite sign. Okay, and at t equals 2, the particle q is at rest. At time 2, is particle p moving toward particle q or away from particle q? So some questions you want to be asking yourself is, where is particle p and where is particle q, and which directions are they moving? We know that q isn't moving, so then we have to answer where is p moving. But again, we first have to know where they are at. And so in this case right here, we have to use their position functions. So we have to know where particle q is, and we have to know where particle p is. So at t equals 2. So let's talk about q. So xq of t, that's going to be equal to, I can plug in 2 right here, or let me go ahead and plug in 2. 2 is going to be equal to, so if I plug in 2 here, I'm going to get 8, and then I'm going to get minus, if I plug in 2 there, that's going to be minus 12 plus 5, and so that's going to be equal to 8, 9. Is that going to be equal to 2? 8 plus 5 is going to be equal, or is that going to be equal to 1? I'm so bad at addition. So, yeah. Okay, that should be equal to 1 then, right? Okay. So then we need v, or we need xp of 2. So you're going to have to plug in 2 right here. So if I plug in 2, that becomes 2, that becomes 2, that becomes 2, and that becomes 2. But if these become 2, these just become 1. So it's going to be equal to 1 minus 4 over 1 plus, is that going to be, so if I plug in 2, just 6 right there, right? So is that going to be equal to, wait, if I plugged in 2, right? I'm plugging in 2 minus 2, that's going to be 1. Plugged in 2, 1 minus 4. Yeah. So it's going to be equal to negative 2/3, right? Why do I feel like I got different answers whenever I was doing the key? I don't feel like these are the same answers I got when I was doing the key. But then I don't know which one's correct. In any case, yeah, I'm going to check with my calculator. How about that? If I got a calculator, why not just check it? So we're plugging in 2 to store as x. So if I plug that in here, so let me type in the function. So I'm going to get second e raised to the 2 minus x, and then we're going to get minus 2x. My gosh. Yeah. Yep, that's equal to negative 3. Yep, because 1 minus 4 is negative 3 and not negative 2. Okay, yep, I know this right here. Oh, man. E raised to the 2 minus x, and then we're going to do plus 3x, and that's going to be equal, oh my gosh, wait, let me go back a second. What in the world was I thinking? I have no idea how I got this. What in the heck, man? It's equal to 7, and then that's equal to negative 3. Wow. Thank goodness for calculators, right? Good thing I always let you guys have them. So negative 3 over 7. Okay. Yeah. All right. So is that everything I need? But then I need these. So let's see. 1 second. I'm making sure I'm getting the other one right too, since I was so off on my last one. X to the third minus 3x squared plus 5. Yep, that's equal to 1. So I got that one right. Okay, so if I have the x-axis here, which both particle and p and q are on, so this is the x-axis. Okay, at time t equals 2, particle q is going to, I'll call this 0. We'll say particle q is right here at 1. So this is where particle q is. And particle p is going to be over here. So this is particle p. So I know that this particle is at rest, but I need to know if this one's moving left or moving right. So that depends on the velocity. So I'm going to plug 2 into here. So Vp of 2 is going to be equal to negative 10. And then if I plug in 2 here, that just becomes 1. And then that's going to be negative 10 minus 5 over, and then if I plug in 2 here, this becomes 1. So it's going to become 1 plus 6, and then that's going to be squared. So that's going to be equal to squared, so negative, so this is going to be negative 15 over 49, right? So in any case, it's negative. So we'll say this, Vp of 2 is less than 0, which means this particle is moving left. And so we are moving away from particle q. So moving away because p is left of q and moving left. There you go. Okay, so for 21, describe the position of particle P and the position of particle Q as t approaches infinity. So the limit as t approaches infinity, let's start with P. So the position of P. So that's going to be xp of t. and xp of t is that equation given there. So we're going to do the limit as x approaches infinity of e to the 2 minus t minus 2t over e 2 minus t plus 3t. So we're going to see what is the position going to. As time increases to infinity, what's happening with the position of particle p? Where is it going? And so let's see here. So if I apply as t approaches infinity, so again, I can kind of see that it's negative here. And so if I plug in infinity, this is going to approach 0 because it's going to be like 1 over, yeah. So this is going to be 0, and then this is going to be 0, but this will be infinity. This will be infinity. Oh man, I should make good examples I should be setting the example. We have to do this separately because it's a free response question. So it's going to be equal to 0 minus infinity. And then if I do the limit as t approaches infinity of e to the 2 minus t plus 3t, that's going to be equal to, again, 0 plus infinity. And so we get negative infinity over positive infinity, which is an indeterminate form. Okay, so then we have to use L'Hopital's rule, the limit as t approaches infinity, and the derivative of this right here is going to be negative e to the 2 minus t minus 2 over negative e to the 2 minus t plus 3. And again, as I apply the limit, that will be 0, that will be 0. So I'm going to be left with negative 2 over 3. So the position of particle p as time increases to infinity, eventually particle p is just going to approach negative 2/3. Okay, and then let's do the limit as t approaches infinity of particle q, and particle q's position is given by x to the, or t to the third minus 3t squared, right? Plus 5. So what's going to happen to this particle right here as it approaches infinity? That there is going to approach infinity. So the particle of Q, so basically if we think about it here, particle Q is just going to keep going that way. It might do some back and forth initially, or it might do some back and forth initially, but it's eventually just going to keep going to infinity. This particle right here might do this and that, not really sure, but eventually it's just going to go towards negative 2/3. So not very far from where it is now, or where it was at t equals 2. Okay, and that should be everything for this review. Hopefully this was a good enough video, and good luck.